Okay, so the plan for today is to finish up a couple of examples in section 4 or 5, adding and subtracting fractions with unlike denominators, and then move on to 4, 6, and 4, 7, possibly finishing up all of chapter 4 today, or we might leave a couple of problems in 4, 7 for next time. I do have quite a few administrative details to sort out. So let's get started on that. So first things first, the Unit 1 exam grades are updated. So from the exam that was uh, due 2 Sundays ago, they're updated as of last week. So if you haven't seen your updated Unit 1 exam grade on WebAssign, check WebAssign, and most folks got some points added. Not everybody got points added, right, for partial credit. I mean, particularly if you got a pretty high score, there's just, not a lot of opportunity for partial credit, but that's kind of a good thing because that means you got full credit on a lot of things. But you can check your grade and see if it was updated. I think on your end, on my end, it shows up with a little asterisk whenever the grade is updated by me. I think maybe on your end, it'll either show up with an asterisk or maybe like a parentheses to show how many points were added or something like that. So I think you can tell in the grade book if your grade was updated. If you have questions about the details, I always put notes in um, to explain like what problems got extra credit added. But unfortunately, I don't think you can see the notes that I put in on my side. So if you have questions about the details, hey, I see I got 7, points for partial credit. What was the allocation? Just either shoot me an email, stop in office hours or something. I'm happy to give you any of those details. So if you have any extra questions, unfortunately, like the my lab system, like my math lab or my stat lab or my econ lab, whatever, um, those ones I can go through and problem by problem change the grade. And in WebAssign, I can't change a problem by problem. I have to just kind of keep my own notes and then make an adjustment to the overall assignment grade. So that makes it a little harder to tell on your side what's going on. But again, if you have any questions, just ask, and I'm happy to provide any of those details to you. Another note is this week, I'll be posting midterm course grades. You can find those on the portal. So my.ccac.edu and go into I think it's like view my grades tab, something like that on the student side. They're always changing the wording of the portal a little bit, but it's something along the line of view my grades. And you can see your midterm course grades there. So quick note on midterm course grades. And I think these notes definitely apply to my course, and I think I can pretty confidently say that they probably apply to every course. And I think most faculty, even if they don't really explicitly tell you this, I think most of them would agree with these sentiments. Midterm course grades are kind of tough for faculty to decide, what the midterm course grade should be. Ideally it's supposed to be something that's like a a gauge of how you're currently doing in the course. But that's a very amorphous statement, right? Um, to make it a little more precise, it's probably something, the goal would probably be something like if you continue putting in the level of effort that you've put in to this point in the course for the rest of the semester, what do I think your final course grade would be? But that's a very difficult question to answer, right? I mean, obviously, the difficulty of the material is not consistent over the entire course. Typically, the beginning material is a bit easier than the material closer to the end of the course or even in the middle of the course. Um, and people's personal lives and academic lives and so on change over time. So if you have a whole bunch of projects and papers that hit all at once, that's gonna, putting in the same level of effort that week versus some other week, you're gonna have to put in more effort that week to maintain a good grade on that. So these midterm course grades come with a lot of caveats. Um, so the way that I will compute your midterm course grade is I'll take the Unit 1 exam grade, and I'll do a weighted average of that with the average of your homework the average of the homework sets that were due as of this past weekend. So all of the homework sets that are past due, I'll take the homework average, take your Unit 1 exam grade, take a weighted average of the two, weighting according to the weighting in the syllabus, and that will be your midterm course grade. So what what that kind of means is that midterm course grades aren't super precise or super granular. So if you feel like you're doing B work and you see a midterm course grade of C, or you see a midterm course grade of A, don't be thrown off by that, right? If it's pretty close to what you expect, then it's probably in line with expectations. Um, on the other hand, if you think you're doing B work and you see a midterm course grade of D or F, that's something to probably be concerned about. If you think you're doing terribly in the course and you see a midterm course grade of A or B, well, that's something to also, take into consideration. Um, maybe there's a bit of a disconnect in that direction as well. So if you're a couple grades away from what you expect, maybe that needs to warrant some consideration, or maybe you can reach out to me and, we can have a chat about it. But if you're like, one grade away from what you expect, midterm course grades aren't all that fine detailed. So that's my spiel on midterm course grades. I think they can very easily be misinterpreted, and a student will see a B on their midterm course grade and they think that that means that they're like almost in some sense like guaranteed to be in the course at the end, and that's not how it works. So um, it's just a very rough estimate of where you probably are roughly at this point in your in the course. Um, I honestly think the best way to evaluate how you're doing in a course is to do a scenario analysis. And what that means is you look at how the final course grade is computed in the syllabus and you do the computations under different scenarios. What if my Unit 2 exam grade and my final exam grade turn out to be the same as my Unit 1 exam grade, and my homework average stays the same as it is now? What would my final course grade look like then? What if I was able to boost my Unit 2 exam and final exam grades by, 5 percentage points, and I could increase my homework average by, 10 percentage points? What would my final course grade look like in that scenario, right? Or what if they went down? You could do a couple scenarios like that and see, some different scenarios. What is your final course grade going to look like? So I think that's probably a better way if you're actually assessing your own standing in the course, probably a better way to go about it. Um, but that also requires a lot of introspection on your part. Am I going to be able to keep up the same level of effort as the first half of the course? Am I going to be able to ramp up effort? Or things coming up in my life or in my academics that I have to actually cut back on effort a little bit. Um, so that's a much more individualized approach that you could do if you want to. And then the last administrative detail is I did meet with our point person for ProctorU last week. And I mentioned that, there were some tech challenges with ProctorU. We switched from Examity that we had used up through the end of the summer to ProctorU, our new proctoring system this semester. Had some tech challenges. So I did not roll it out for the Unit 1 exam because I didn't want, it's already stressful to take an exam. I didn't want you going through and encountering any of these tech problems while you're trying to focus on an exam. So unfortunately, those tech challenges still exist and are, I think, possibly um, even more cumbersome maybe than I expected. And we don't really have a workaround for them. But nicely, we do actually still have access to the Examity proctoring system. Our folks at CCAC pushed and got us that. So we're going to be using Examity, the kind of tried and true system. We'll be using the automated option on Examity. It's very reliable, very robust. I will post an Examity practice exam in the next day or so, either today or tomorrow, and I'll post a Blackboard announcement along with it. Note that the Examity practice exam, when I post it, the sole purpose of that exam is for you to get onto the Examity system, to go through Blackboard into Examity, create an account, learn how to kind of start up a session, a testing session, and all of that. That's really the sole goal of the Examity practice exam. I put some dummy questions in a dummy exam on WebAssign, it's not meant to prepare you academically or assess you academically. I didn't even really worry about whether the number of questions I put in there could reasonably be done within the amount of time that I gave you. It's just meant to get you through the examining process once so that you're familiar with the process. And then whenever you go to start up examining on the actual exam, you'll be familiar with how the technology works. You'll have gone through it once already. You'll have ensured that it works for your computer, your webcam, your browser, all of that, that all works. So keep an eye out for that. And like I said, I'll post the Blackboard announcement as well. It'll be copied to your email and it'll have a lot more information about the details. So I would recommend doing that examine practice exam pretty soon, this week or next. I know we don't have an exam coming up for the Unit 2 exam coming up for a little while, but getting that squared away early is better because if you do encounter a tech problem, then that gives us a lot of time to figure out a solution. If you wait until, the week before the exam or even worse, the week of the exam to complete it, and then there's not a lot of buffer. If something goes wrong with, with your computer or your webcam doesn't work with it or something, um, then you know when you go through the practice exam, find that out, you have a lot less time to remedy that before the close of the Unit 2 exam window. So get it done early, get things worked out. For the vast majority of people, they have no problems at all. And for the people who have problems, which happens occasionally, usually we're able to sort it out pretty quickly with maybe just one email. It's not going to be due at a certain time, but again, I'd recommend that you do it in the next week or two. I'll probably set the due date to be like the end of the Unit 2 exam window. So, several weeks from now, but I would strongly recommend doing it in the next week or so, next week or two. What should you do if your camera is broken? I mean, you can reach out to me, but one of the requirements for the course is to have an operational web camera. So that's in the syllabus. You can buy a webcam on Amazon for 20 to 25 bucks, something like that. Or Best Buy, something like that. Or I can put you in touch with one of the deans of students, and they sometimes have the ability to work with students and get you the technology you need for the course. There might be an option for you to come onto campus and take the test there. So there are some different options if the tech is an issue getting that sorted out. Okay, so yeah, so keep an eye out for the examity, practice exam and announcement in the next day or two. Um, but I think that is all of the administrative stuff that I wanted to cover. I know it was a lot of details, but hopefully that clarifies these different things that are going to be coming up this week. The quote of the day is by the Roman Emperor Marcus Aurelius, sometimes just quoted as be one. But that also kind of sounds like, be one with the world or something, which wasn't really the point. This comes from a longer quote. Stop arguing about what it means to be a good man, be one. So in other words, it's much more comfortable to sit here and debate things philosophically, and this is certainly a trap I fall into, right? Is we can debate philosophically about what it means to be a good person, or maybe debate philosophically about what the best study strategies are, or whatever it may be. But if we never take a step forward, we never really get anywhere. So usually in most circumstances, enough to take a couple of steps forward and start implementing the practice rather than continuing to plan or continuing to optimize or something like that. So start taking a couple of steps forward and start implementing rather than continuing to plan, I think is kind of the thrust of this idea. And kind of interestingly, Marcus Aurelius was a Roman emperor, but he wrote in Greek. Um, and there's always a debate among the classicists about, what's cooler, the Greeks or the Romans, or the Greek language or Latin. And, all that I'll say about that is, well, you have a Roman emperor who wrote in Greek. So I think that makes the answer pretty clear, but that'll that'll fire up some classicists if you tell them the Greeks are cooler than the Romans. All right, so moving on to 4-5, adding and subtracting fractions with unlike denominators. We're actually going to go back and we worked through quite a few problems on this topic last time, but we're going to go back and we're actually going to do a couple more of those problems. Just because when we have a complex topic, I kind of usually like to split it up over 2 days. So you kind of get an introduction to the topic, get to work through the topic, get to take a couple of days to digest it, maybe work through some homework problems or practice problems, and then come back and see it again. Sometimes you just have a little bit of a different perspective the second time around. So we'll do a couple of kind of warm up or review problems, and then we'll jump into the end of 4-5 and continue on from there. All right. So let's start with this one. Simplify 3/2 minus 7/9 plus 4/6. I notice that I have addition or subtraction of fractions with unlike denominators, 2, 9, and 6, not the same denominator. So we have our pizzas that are, one of them's sliced in slices of half pizzas, one of them's in slices of 1/9 pizzas, and one of them is in slices of 1/6 of a pizza. And we need to figure out how to cut all of these different slices up to end up with slices all of the same size that we can accumulate together nicely. And what's our goal? We want to find the LCD, which is the LCM of the denominators, the least common multiple of 2, 9, and 6. And remember to find least common multiple, we first write out the prime factorization. Well, 2 is just prime, so it's just 2. 9 is 3 times 3. And 6 is 2 times 3, so I'll write the 2 under the 2's column there. And then times 3 under that 3's column. So my LCD is 2 times 3 times 3, or 18. Remember, the idea here was like if I needed to give you a Lego set, the smallest possible Lego set, so that you could build a 2, or you could build a 9, or you could build a 6, not all at the same time, but you could build a 2, take it apart, build a 9, take it apart, build a 6. I would need to give you one Lego of size 2 and 2 Legos of size 3 to do that. That's the idea here. Or that's an LCD of 18. So I want to convert each of these fractions into an equivalent fraction with a denominator of 18. And I do that by multiplying numerator and denominator by the same number using our equivalent fractions property. And I know that 2 times what pieces is 2 missing? It's missing a 3 times 3. 2 times 9 is 18. But I need to multiply the top by the same number. What is 9 missing? 9 is missing a 2. 9 times 2 is 18. Multiply it on the bottom, but I need to multiply the top by the same number. And then again, I have a 6. What do I need to multiply it by to make 18? It's missing a 3. Multiply it on the bottom. 6 times 3 is 18. But I better multiply by that on the top as well. Now I simplify each of these. 9 times 3 is 27 divided by 18. Minus 14 eighteenths plus 12 eighteenths. And now I'm in a situation where I have addition and subtraction of fractions with like or with common denominators. All of my slices that I originally had, some of them were big slices like half a pizza, some of them were small slices like 1/9 of a pizza. Now all of those slices, I've recut them up so that I have a bunch of 18th slices of pizza. I can just combine those all together under one fraction. 27 minus 14 plus 12, all over 18. Well, minus 14 plus 12 is just minus 2, right? 27 minus 2 is 25. And I can either leave my answer as an improper fraction like this, or I can make it a mixed number. I see that there's one lot of 18 and 25, and I'm left with 7/18 left over. Okay. If I look at this next problem, negative 11/30 minus negative 27/40. Maybe the first thing I'll do is I'll kind of resolve these two negatives. I'll make it a plus 27/40. Okay, that makes it a little simpler to deal with. I just have the sum of two fractions now. Well, again, I have fractions with unlike denominators, so let me come over here and look for the least common denominator. So I'll take my denominators 30 and 40. I'll get a prime factorization. Well, 30 is 6 times 5, and 6 is 2 times 3. So 30 is 2 times 3 times 5. And 40, well, I guess 40 is like 4 times 10, maybe is an easy way to break it up. 4 is 2 times 2. 10 is 2 times 5. So 40 has one factor of 2, which I'll write under the factor of 2 belonging to the 30. It has one factor of 5. And it has two more factors of 2. So in other words, if I only gave you one Lego block of size 2, you could build a 30 with some others. But if you only had one Lego block of size 2, you couldn't build a 40. So we need to give you a couple more Lego blocks of size 2. So what's my LCD? It's going to be 2 times 3 times 5 times 2 times 2. I'll put those two together. 5 times 2 is 10. 2 times 3 is 6 times 2 is 12. Or that's 120. My lowest common denominator is 120. So I want minus 11 over 30, and I want to multiply top and bottom by something to get a denominator of 120. I see that the 30 is missing these two factors of 2 that were needed to make the 40. So I need to multiply by 2 times 2 or by 4. 4 times 30 is 120, so that looks good. And I better multiply on the top as well. And similarly, what's the 40 missing? The 40 is missing the 3. So 40 times 3 is 120. I multiply that on the bottom. I better multiply by that on the top as well. Or I have negative 11 times 4 is 44 over 120 plus, well, 27 times 3. So I could multiply that out over here. 3 times 7 is 21. 3 times 2 is 6 plus 2 is 8. So that looks like 81. And now I've gotten to the point where I only have the sum of two fractions with common denominators. Now I can just add the numerators together. Negative 44 plus 81 over 120, or this is just 81 minus 44 over 120. I'll make this a 7 and 11. 11 minus 4 is 7. 7 minus 4 is 3. 37 plus 44, that is 81. That looks good. So we have 37 over 120. We can evaluate an expression with fractions. It works the same way as evaluating an expression with whole numbers or natural numbers or integers. If we want to evaluate 7/10 minus w, when w is 1/2, That's just going to be 7/10. Everywhere I see a W, I replace it with 1/2. This one might be easy enough that I can just do in my head. I don't have to do the whole LCD thing. I noticed that if I multiply the denominator of 1/2, the 2 by 5, I get 10. So I might recognize that 1/2, well, that's just 5/10. Right? So when you get, used to this, it goes a little more smoothly. Or if you recognize a certain pattern, or if you see that you can multiply one denominator to get the other by some number to get the other denominator, right? So you can take shortcuts if you see them. Just be careful that they're actually valid shortcuts, right? We didn't, you know, take some kind of crazy shortcut like 7 - 1 over 10 - 2 or something. All we did is cut out the whole writing out the prime factorizations and all that because we noticed that we can multiply 2 by 5 to get 10 and our denominators will be the same then. 7 - 5 is 2. And 2 divided by 10, well, that's 2 divided by 2 times 5. Let's say 2 times 1. This gives me 1/5. Then last problem in this section. What if I have a fraction expression with variables in it, with say x's in it? I have 3x minus 5x over 9. When I say enough, not much changes. I see my lowest common denominator is obviously going to be 9. It's the only denominator around. So I need to convert this fraction, 3x, or what's really 3x divided by 1, into an equivalent fraction with 9 in the denominator. Right? So my goal is to get a 9 in that denominator. Well, 1 times what gives me 9? That's got to be 9. I better multiply it on the numerator as well so I don't change the value of that fraction. And then 3x times 9 is just 3 times x times 9. But multiplication is commutative, so I can make this 3 times 9 times x, no problem there. And 9 times 3 is 27. Now I'll simplify my numerator. I have two like terms. They both have the same variable x to the same power, the first power. We don't write it when it's the first power, but it's like x to the 1 power. We could think of it that way. So then we add or subtract the coefficients and combine the like terms. 27 minus 5 is 22. And we end up with 22x over 9. That x didn't really materially do anything. It just kind of came along for the ride. Any questions on adding or subtracting fractions? So I know for a couple of these, we went a little bit more quickly through it than we did last time. But again, having introduced it last time, hopefully you had worked on some practice problems or homework problems over the weekend. This is the second time we're seeing it. So it's, a little bit more of a review than introducing it the first time. Okay, so let's move to the next topic then, using order of operations to simplify complex fractions. So we talked a little bit about complex fractions already, where we have fractions that have as the numerator denominator fractions. So a fraction that has a numerator denominator, but where either the numerator denominator or both are themselves fractions. Well, now we have fractions where the numerator denominator might be slightly more complicated expressions. We've seen something like this before. We've seen this in past sections. But now those slightly complicated expressions in the numerator or in the denominator might actually involve fractions themselves. So I know that when I have an overall fraction like this with a numerator of 2 and a denominator of 1/3 plus 1/5, my goal is to first simplify the numerator. Well, there's nothing really that can be simplified there. Then simplify the denominator. I can do this fraction addition and make this one fraction, and then simplify the overall fraction. So my denominator, 1/3 plus 1/5, well, I know that 3 and 5 are both prime numbers. So my lowest common denominator is going to be 3 times 5, or 15. I have to multiply 3 by 5 to get 15. And I need to multiply 5 by 3 to get 15. Or this is 5 plus 3 over 15, or 8 over 15 for the denominator. So my denominator ends up being simply 8 over 15. My numerator is 2, but maybe I'll choose to write it as 2 over 1 divided by 8 over 15. And again, remember that the fraction line just means divided by. And so I have 2 over 1 divided by 8 over 15. I have a quotient of two fractions. And when I have this situation, I invert and multiply, right? I multiply by the reciprocal. I take 2 over 1 times 15 over 8. This gives me 2 times 15 over 1 times 8, or that's 2 times 15. 1 times 8 is just 8, and 8 is 2 times 4. My 2's divide out, I get 15 fourths. And again, I can either leave my answer as an improper fraction, or I can say 4 goes in the 15 3 times with a remainder of 3. So I can say this is 3/4, 3 3/4. So just depending on what the problem asked for, or what made it easier for you to work with for whatever application it is, you can leave it as 15/4 or 3 3/4. We could even build up to a problem like this one. This looks quite complicated. In my numerator, I have 3/4 plus 1/2. In my denominator, 5/6 minus 2/3. So, it looks more complicated, but the strategy is still the same. I've isolated my numerator and denominator. I'll look at each of them individually, see if I can simplify them. If I can, I'll simplify them as much as I can. Then I'll put them back as a fraction, numerator over denominator, with a simplified numerator and denominator, and look for even further simplification. 3/4 plus 1/2, the lowest common denominator is going to be 4, because 2 times 2 is 4. So I need to multiply the denominator of 2 and the 1/2 by 2 to get 4. And that means I better multiply the numerator by 2 as well, so that I'm respecting my equivalent fractions property. Or this is 3/4 plus 2/4. That gives me 5/4. So that is what my numerator is, 5/4. My denominator also a difference of fractions, so subtracting fractions with unlike denominators. But again, I noticed that 3 times 2 gives me 6. I can actually just convert this 2/3 into some number of 6. Basically, I'm taking each of these bigger slices of pizza that each represent 1/3 of a whole pizza and just cutting them in half so that they represent 2/6 of a pizza each. I want to multiply by 2 on the bottom so that I get a denominator of 6. And I need to not change the value of the fraction to respect the equivalent fractions property. I need to multiply by the same number in the numerator as well. So 2/3 is the same as 4/6. And I have 5/6 minus 4/6. 5 minus 4 is 1. And that's 1/6. That is my denominator. So this whole fraction, what does it turn out to be? It turns out to be 5/4 over 1/6. And again, I can think of this as 5/4 divided by 1/6. If I write it this way, it's a little clearer what the next step should be. I want to invert and multiply. 5/4 times 6 over 1, or that's 5 times 6 over 4 times 1. And I look at this, 5 is prime, 6 is 2 times 3, and 4 is 2 times 2. I can divide out one factor of 2. I get 5 times 3 is 15 halves as my answer. Or again, I could write this as 7.5. Could write it that way as well. So these problems look really complicated. You know, if you walked up to this and you looked at it, you might think, oh, I have no idea how to solve that. It's too hard to do. But again, if we take it step by step, say, okay, it's just one big fraction that has some denominator and some, well, if I can select it, and some numerator. Let me look at the numerator by itself. 3/4 plus 1/2. Oh, okay, I know how to do that, right? I can make that happen. It's ends up being 5/4. If I look at the denominator by itself, again, I get 5/6 minus 2/3. Not a trivial simplification, but I can do it. I know how to do that. Ends up being 1/6. I plug both of those back in and I end up with the ratio 5/4 over 1/6, or 5/4 divided by 1/6. But I've also figured out how to do division of fractions with the inverted multiply or multiply by the reciprocal idea. And then I get my way over to here where all that I have left to do is just divide out any common factors and write my answer. So there are a lot of steps. There's a lot of individual manipulations, but we can see the strategy. We can see that the strategy is the same for a more complex problem like this one, where there's a lot of individual steps, versus for a simpler problem in the same vein where there are fewer steps. Now, when we have a lot of steps, we just have to take extra care to, you know, be pretty diligent, try not to make mistakes, try not to make silly errors, right? Just make sure that every operation that we do is supported by one of our properties or one of our methods that we've discussed before. So I don't want to, do something like 5 minus 2 over 6 minus 3 and just get lazy or flippant with my properties. Fraction subtraction doesn't work that way. So we need to use our, for instance, equivalent fractions property to get a common denominator. But as long as we're careful about things, we can make it through step by step. And kind of as a side note, from the other point of view, if you're looking at this and thinking, I have no idea what the strategy is, the overall strategy, sometimes just taking a step forward can help. Is there something you can do? Well, I see that I have a 3/4 plus 1/2, which I'm really having trouble selecting for some reason. Um, can I do something with that, right? Even if I don't see the whole end path to, or the whole path to the end goal, maybe there's one thing I could do to move forward. Now, maybe I go down this path and it turns out to not be the right path, and I have to reverse back and try a different path. That could happen. But if nothing else, I've learned a little more. I've learned that that wasn't the right path to go around, and I have one fewer, wrong direction to turn. But I can do something, right? So sometimes with a problem like this, if you get stuck, especially on an exam, sometimes just asking yourself, is there something I can do? Is there one step forward that I can take? And sometimes taking that one step forward just kind of unlocks things a little bit, or if you move one step forward, maybe that gives you a different perspective on the problem. You see that something's going to simplify a certain way and you say, oh, okay, I kind of see where to go now. Or maybe you just take one step forward and you still aren't really seeing the whole strategy. Can you take one more step forward? Is there one more thing you can do? Is there one more thing you can simplify, or you know that you can, one more operation that you can do, that you can perform? Okay, so let's move on to adding and subtracting mixed numbers. So let's model these following three problems. So we have 1 3/8 plus 1 7/8. So we have one whole, and then we have a pizza sliced into eighths, and we have three of those. So that's my 1 3/8, and then plus 1 7/8. These can take a little bit of time to draw out. So there's my 1 7/8. And I want to add them together. So I'm having a pizza party and somebody brings a whole pizza plus 3/8 of a pizza. Maybe they ate 5 slices on the way over. And somebody else brings a whole pizza and 7/8 of a pizza. They ate one slice on the way over. How much total pizza do we have? Well, I can split out the wholes. I can kind of split those off and then add up the fractional bits, which I'm just going to kind of draw schematically like this. So I can add up the wholes, 1 plus 1, and add up the fractional bits, 3/8 plus 7/8. And that's kind of how we do mixed number addition. We add the wholes together, and then we add the fractions together. Now, sometimes it turns out that if I have 3/8 plus 7/8, that's going to make one whole. And 2/8, right? If I imagine combining these two pictures together, this slice is going to fill in that gap, and then I'm left with two extra slices. So this one whole can actually kind of get accumulated onto the other wholes. Or this gives me three wholes and 2/8 left over. Or I might decide to simplify this 2/8. I see that I can really think of it as just 1/4 slice of pizza. This 2/8 is 2 times 1 over 2 times 4, just 1/4 with our equivalent fractions property, or with looking at the model. I was given the question in mixed numbers. I probably should answer in mixed numbers. That would be sensible. So in all, I have 3 1/4 pizzas. Sometimes I put my fractional parts together and they make a whole, and that can get lumped in with the other wholes. Sometimes I put the fractional parts together and it stays a fractional part, right? If I had 3/8, 1 3/8 plus 1 2/8, I would end up with 2 whole pizzas and then 5/8 of a pizza from the fractional parts. So when I'm adding mixed numbers, I just add the wholes, add the fractional parts together, and occasionally my fractional parts will make another whole and I'll add that onto the wholes. What about when I'm subtracting? 2 7/8 minus 1 3/8. You know, it takes a little while to draw eighths, but I try not to use the same denominators all the time. So 2 7/8. And then minus, or we'll draw these in red, minus 1 3/8. So take away 1 3/8. So what does this mean? This whole green, one of these cancels with that whole red. And 1 2 3 greens cancel, green slices cancel with 3 red slices because they're the same size pieces. They're both they both are in increments of 1/8 of a pizza. So I've got rid of these 3 slices, which is what those 3 slices there told me to do. And I got rid of my 1 whole pizza. What am I left over with? I'm left over with 1 whole. And I have 1 2 3 4. I'll kind of rearrange them this way, maybe. So I'm left over with 1 and 4/8. Well, I also kind of see that that is just a half a pizza. Oh, that's just 1 1/2. 4/8 is 1/2. 4 times 1 over 4 times 2. The fours divide out and give me 1/2. Okay, so I don't think either one of those was too bad. What about something like this? 3 3/7 minus 1 4/7? Let me redraw those division lines there. So there we go. Maybe not the prettiest, supposedly equal sized pieces, but pretend that those are 7 equal sized pieces. 1 2 3 4 5 6 7. Yeah, there's 7 of them. And I have 3 of those. And I want to take away 1 and 4/7. Okay, so if I start canceling out my fractional bits, I can use one of the green slices. These are all in sevenths, right? To satisfy one of the red slices. They kind of come together and make what's essentially a neutral pair of sevenths, of 1/7 slices. I can do that again, and I can do that again. But here, I've run out of green 1/7 slices that I kind of have in my possession, and I still kind of owe a 1/7 slice. I still kind of need another green 1/7 slice to cancel out that remaining red one. So what should I do? Well, what I'm going to do is I'm going to take one of my whole pizzas that I have, and I'm going to split it into 7 pieces. Is that 7? Yeah, 7 pieces. So now I've got all of these pieces from one of my holes. And now I've got 7 more 1/7 slices, and I can use some of these to satisfy the remaining red ones. I can take this green one, match it with that red one. That's a neutral pair. They go away. And now I've satisfied all of my red fractional parts. I also see that I have a green hole minus a red hole. I can get rid of those. So I've gotten rid of all of my slices from the original fractional bit. I've gotten rid of one of my green holes, and another green hole was broken up into 7 slices to allow one or more of those slices to mesh with the reds that I needed. So what am I left with them? And all of the reds are canceled out now. So I've satisfied all of the reds. So I'm left with one whole pizza. And then I have what? 1, 2, 3, 4, 5, 6, 1 and 6/7. So up here, procedurally, what did we do? We basically took like 2 minus 1 for the wholes was 1. And we took 7/8 minus 3/8. We subtracted the wholes, we subtracted the fractional parts, 4/8, and then we just kind of put them back together and then simplified. But we see that sometimes that's not going to work so well, because if I have 3/7 minus 4/7, that gets a little complicated. So maybe the first thing that I'll do in either case, whether I'm adding or subtracting, is I'll look at my fractional parts first. I'll look at 3/7 minus 4/7. And I notice that this is going to be a negative number. This isn't going to work out well. So I have to borrow, right? So 3 and 3/7, I could rewrite that as, well, that's like 2 and 7 plus 3, or 10/7. Right? Where is that coming from? Well, from the pictures, but also 3 and 3/7. What does this really mean? This really means like 3 plus 3/7, right? But 3 I could think of as 2 plus 1, the 2 holes that I want to keep as holes, and then the 1 hole that I want to break up. And I could ask, if I look at just that 1 plus 3/7, how could I write that in terms of a common factor or a common denominator? Well, 1 would be 7/7, and 7/7 plus 3/7 is 10/7. Or 2 plus 10/7 is just 2 and 10/7. I could write 3 and 3/7 as 2 and 10/7. So because I see that 3/7 minus 4/7, I don't have enough 7th slices that I in my possession to satisfy the 4 that are demanded of me. I can rewrite this as 2 and 10/7 minus 1 and 4/7. And now if I have 10/7, and need to give away 4. Well, now I can do that. That's 6/7. So now I can subtract the wholes. 2 minus 1 is 1. And 10/7 minus 4/7 is 6/7. So when we're subtracting, the first thing we'll do is check if we need to borrow. And if we do need to borrow, then we'll do an operation like this. If we don't, then we can just subtract the wholes and subtract the fractional parts. If we do need to borrow, we borrow, and then we subtract the wholes and subtract the fractional parts. And in addition, we just add the wholes and add the fractional parts, right? Adding the wholes gave me 1 plus 1 was 2. Adding the fractional parts gave me 3/8 plus 7/8 was 10/8. But that's really 1 and 2/8. So now again, I want to add 2 plus 1 and 2/8, or that's just 3 and 2/8, or 3 1/4. So we can think about this according to the model, or we can think about it in terms of something a little more abstract, but that's going to generalize to problems with to bigger problems with bigger numbers a little more easily. So let's go through several examples of these. Okay, let's simplify this using mixed numbers. Well, I have an addition problem here, so I know that I don't have to do any of this, borrowing or anything like that. So let me start with breaking this down. I have my wholes, 4 plus 9, and my fractional bits, 5/8 plus 3/8. Well, 5/8 plus 3/8 is 8/8, or that's just a whole of 1. Because I've made a whole out of the fractional parts, I'll kind of just tack that up here. That's almost like carrying a 1, right? Is really what we're doing here. And 9 plus 4 is 13, and plus 1 is 14. So this is 1 with a remainder of 0. It has 0/8 left over. In fact, this is just the number 14. If I were to look at, say, 3 4/5 plus 6 4/5, another thing that I can always do, we can work with the mixed numbers as they are. Sometimes this works out really nicely. Sometimes it's quite complicated. Another thing I can always do, remember, I can always convert mixed numbers into improper fractions and back and forth. I could say, instead of doing 3 4/5 plus 6 4/5, 4/5, instead of working with the mixed numbers as they are, I could choose to convert them to improper fractions first and do whatever operations I want to do in improper fractions. 5 times 3 is 15, plus 4 is 19. So 3 4/5 is the same as 19/5. 5 times 6 is 30, plus 4 is 34 over 5. 6 4/5 is the same as 34/5. But now I can just add the improper fractions. This is 19 plus 34 divided by 5. Or that's 33 plus 20. If I take 1 off of the 34 and put on the 19, 33 plus 20 is 53 over 5. And I see that 5 goes into 53 10 times with a remainder of 3. So that's going to be 10 3/5, converting back to a mixed number. So that's another option that I have, right? We could have, if you want some practice, do this problem, but convert to improper fractions first, and then do your addition in improper fractions and see what you get. Or do this problem by mixed numbers, just do it in the mixed number setting. Add the fractional parts, bring any wholes up and add the wholes together along with any wholes that came from the fractional parts, and then get your answer. And you should get the same answer in both cases, doing it the other way, doing this one with improper fractions or this one with mixed numbers. Let's take a look at this one. We have 8 and 17/20 minus 4 and 9/20. So let's simplify using mixed numbers. So here I would first look at my fractional parts. I do have a common denominator. Do I have enough 20ths that I kind of possess to satisfy the ones that are demanded of me? I have 17, 9 are demanded of me. Yeah, I have enough. So 17/20 minus 9/20 is 8/20. I didn't need to borrow anything, so now I just do 8 minus 4 is 4. So I subtract the wholes, I subtract the fractional parts, put them back together, and this gives me 4 and 8/20. Or, of course, when we saw that 8/20, we probably would say, well, I see there's a factor of 4 in the top and bottom. That's 2 over 5. So that wasn't bad. What if I wanted to do this with improper fractions? Well, I need to start by taking 8 and 17/20 and 4 and 9/20 and converting them to improper fractions. 20 times 8, well, that's like 2 times 8 times 10, or 16 times 10, or 160, plus 17 is 177. And you can definitely, do the multiplications and the additions and so on off to the side. So if you're able to do some of these in your head, that's good. That's where you should be kind of striving. That's what you should be striving for. But if you're not able to, that's not a big deal. You can always just go off to the side and do a little bit of scratch work. But particularly when we're multiplying by things that have factors of 10 in them, things are just a little bit easier. If I recognize that 20 is 2 times 10, so 8 times 20 is 8 times 2 times 10, or that's just 16 times 10. That's where I got the 160 and then add 17 to that. So minus 20 times 4 is 80, plus 9 is 89 over 20. So 177 minus 89, if I add 1 to both, that cancels out. So that's 178 minus 90, or that's 188 minus 100. I think that's just 88 over 20. Again, you could take this subtraction, 177 minus 89, go off to the side and carry out that subtraction. Or when you get, a little more used to it, you can start grouping things together, right? I can subtract off 100 easily. So what do I need to add on to 89 to make 100? I need to add an 11. If I add 11 to this as well, then I've added 11 minus 11. So 177 plus 11 is 188. Minus 100 gives me 88. So if you see patterns like that, or if you like that strategy, that's the way I think a lot of people would kind of do a lot of this math in their head. They would, find ways to make, factors of 10, things that multiply by 10, or find ways to add or subtract in increments of like 10 or 100 or something like that, because those are easy numbers to add and subtract, or to multiply and divide by factors of 10. And 88 divided by 20, I guess I see that there's a factor of 2 in the numerator and denominator. 44 times 2 over 10 times 2. I can chip away at this. So there's another factor of 2. 22 times 2 over 5 times 2. This is 22 fifths. So this ends up being 22 fifths. And if I convert that to a mixed number, 5 times 4 is 20, with 2 left over. I get the same answer. It was a little less complex. It was a little less difficult as far as the strategy goes, and as far as the kind of theory goes, a little less complex to use improper fractions, because I already know how to do all of the operations in improper fractions. but the details were messier, right? I ended up with all these big numbers that I had to manage. Sometimes keeping it in mixed numbers is nicer because the numbers are just more manageable. I'm dealing with wholes and parts instead of turning all of these wholes into just an absolute ton of little parts and counting them all up. But sometimes, there are benefits to converting to an improper fraction and doing the work over there as well, because this is really just consistent with all of our other fraction work. Two ways to do the same problem. Each one, I think, has its benefits as well as its costs. More theoretically complex, but the details were easier. I got to do 8 minus 4 was 4, and 17 minus 9. Those are easier calculations to do. This one over here, the theory is easier. We could just say for any of these mixed numbers, just always convert to improper fractions, do the calculation, convert back. We could always do that. But the calculations are messier. So there's a trade-off there. Okay, so what about 2 and 5/8 minus 3 and 1/8? First thing I'll do is I'll look at 5/8 minus 1/8. This is a subtraction. I have 5 slices of size 1/8. I need to give away one of those slices. Do I have enough to satisfy what I need to give away? Yes, I do. I have 4/8 left over. And then what about the wholes? 2 minus 3. Well, this is a little complicated, right? I have 2 minus 3 for my wholes, but I probably don't want to do like -1 and 4/8. Let's look at a model for this. So I'm not really sure how I should combine together these pieces whenever I get, some negative bits and some positive bits. Let's look at how this works out. So I have two wholes. And 1, 2, 3, 4, 5/8. Let me zoom in just a little bit on this. Wrote the circles a little small. And then I want to subtract off 3 wholes. Maybe I'll write a third one down here. And 1/8. Okay, so I can start with the fractional bits. I have 5/8. I can get rid of one of those greens to meet up with one of those red 1/8, and that makes a neutral pair. They annihilate one another, they go away. This green hole makes a neutral pair with that red hole, as does this one. But this leaves me with what? This leaves me with one red hole, but not one red hole and 4 red slices, but it leaves me with one red hole and what? 4 green slices. Hmm. So it kind of looks like I can reinterpret those 4 green slices of size 1/8 as just 1/2. And I could split my red hole into 2 red halves. I can get rid of this green half with one of the red halves. It seems like my answer should be one red half, or -1/2 should be my answer. How can we make this work out? So we don't want to just kind of jump in right away and start doing these calculations. I think probably what I want to do is, if we remember when we were adding and subtracting integers, we would have a subtraction problem, and we would first look at what is the sign of the result going to be, and then we would look at what is the size of the result going to be. I see the thing that I'm subtracting off is greater than the thing I'm subtracting from. In other words, I know that my answer is going to be negative. So my answer is going to be like negative, but then the size of the answer, the magnitude, I'm going to flip these. So to remember this from integers, for instance, if I had, you know, what if I had like, well, just, I guess, 2 minus 3, I would say, well, the thing I'm subtracting off is bigger than the thing I'm starting with. So my answer is negative. This is going to be negative, and then I flip the order to find the size of the answer, the magnitude. 3 minus 2 is 1. This is negative 1. We're doing the same thing here. It's the exact same process. It's just that our numbers, instead of being natural numbers or whole numbers, they are mixed numbers. But now if I look at this, if I want to simplify this, I can actually do this. So let me get rid of all my circles down here. I know what I think I think the answer should be. Negative 1/2. Let's see if we get that. So I have negative. Let me just leave that negative off for the time being. We'll just kind of come down here and figure out what is 3 1/8 minus 2 5/8. Well, now if I try to do my fractions, 1/8 minus 5/8, I don't have enough. I don't have enough eighths to satisfy the minus 5/8 that I want to take away. So I'll choose to rewrite 3 1/8 as 2 9/8, taking one of the wholes and breaking it into 8/8, combining that together with the 1/8 we already had, making 9/8 and 2 wholes instead of 3 wholes and 1/8. And this piece stays the same. So now if I look at my fractional parts, 9/8 minus 5/8, I do have enough now that I'm starting with to take away 5. 9/8 minus 5/8 is 4/8. And my wholes, 2 minus 2 is 0. So 4/8 or 1/2. But remember, 1/2 is what I plug back in up here. This was just my scratch work off to the side. This gives me negative 1/2, just like I expected. So just because I'm in mixed numbers, I don't want to forget about all of these previous properties that I had. Right, when I'm doing a subtraction, I want to see, is the thing that I'm subtracting off bigger than the thing I'm subtracting from? If so, make the answer negative and do the subtraction the opposite way. That was something we had done in several sections in the past. That same property applies here, even though the numbers look a little more complicated. We're dealing with mixed numbers, but we use that same strategy, that same property. So properties usually don't go away. They don't often go away. They just, look a little bit different. Where did I get the 9 from? Yeah, so good question. So we have, let me get a little more room here. We have 3 1/8, but this doesn't give me enough slices of size 1/8 to take away 5 of them. So I need more slices of 1/8. Where can I get them from? Well, I can think of 3 1/8. Well, first I can think of 3 1/8 as 3 plus 1/8. But 3, I could take one of those wholes. I have 3 wholes. I could take one of the wholes and split it off. And I'm going to take one of these whole pieces or whole pizzas and cut it into 8 slices. So this 1 turns into an 8/8 plus 1/8. And now I can combine all of my eighth slices together to make 2 and 9/8. All I really did was like when we would do subtraction of whole numbers and we would line them up above one another and we would like borrow from the next place over. That's really what we're doing here. This 1/8 is just kind of like instead of going from hundreds to tens or tens to units, we're going from units to, a smaller division of units to 1/8 of unit. Yeah, so we're borrowing from the one to make 8/8, adding to that the 1/8 to make 9/8, and that gives us enough eighths that we can get rid of 5 of them. Yeah, sure. Yeah, definitely you're welcome. Yeah, that's a good question. So we're really just doing that borrowing process. We're borrowing one of the wholes to give us 8 more eighths than we started with, and that gets added onto the 1/8 to make 9/8, giving us enough to do the 9 minus 5 is a 4. Yep. Any other questions on this material? We're in mixed numbers. There's just a lot going on, right? There are whole number parts, there are fractional parts, and there's all this other stuff we need to remember about what's the sign of the answer, how do we do fraction, addition, subtraction, all of this, right? So there's a lot of components. Each of the components isn't something that's new, but there's a lot of complexity we have to manage. And I know I've said it 100 times so far in the class, but or throughout the course, really. Um, but this is one of those things that, you know, your head is probably kind of spinning right now, and you're thinking, man, how am I ever going to figure this out? Watching me do it's quite confusing. When you do your first 3 or 4 problems, practicing or going through the book or rewriting notes or doing it on your own, it's going to be really hard. It's going to be like, you're probably going to get them wrong at first and have to go back and fix things. But then when you do, problems 5, 6, 7, it's like, okay, I see the strategy. I see the path to the answer a little more clearly. When you do problems 10 through 15, it's like, okay, I pretty much got it. I make a mistake every once in a while. When you're on problems 20 to 25, then you've got it down, right? It's one of those things that you really have to do it yourself. And again, as I've mentioned many times, if you wait until Sunday night and say, all right, it's Sunday at 8 p.m., what do I have due tonight, and try to blast through it all at once, you're never going to get it. That you just can't learn that way. Um, the way to master this stuff is to, touch base with it every day. I mean, ideally 7 days a week, but if you want to give yourself a day or two off, make sure you're at least, looking at this material, even if it's for, 20 minutes on a couple of those days, do a couple of problems, work through a couple of problems, just let yourself have the time to digest it. And also let yourself have the time that if you are working on a problem and you get frustrated with it, well, step away. If you have, if you start the homework on Monday and on Tuesday you're frustrated with it, you can take Wednesday off and come back Thursday. If you start the homework at 8 p.m. on Sunday and you're frustrated with it, well, it's due in a couple hours. Like, you can't really step away, right? That's not a good learning environment. So give yourself that buffer and plan ahead and take it in small chunks. And that's just a much better strategy in general, but definitely for things where there's just a lot of complexity and a lot going on, like mixed numbers. Okay, so now, because things weren't complicated enough already, what if we have mixed numbers where, somebody went to one pizza place and got 3 whole pizzas, and that pizza place cut the pizzas in quarter slices. So they show up with 3 1/4 pizzas, 3 whole pizzas plus one slice that's of size 1/4. Somebody else went to a pizza place, a very strange place that cuts their pizzas in thirds. So somebody else shows up with 6 1/3 pizzas. How do I add these together? Well, nicely enough, this looks like it would be a lot more complicated. Nicely enough, it's kind of the same strategy, right? We're adding 2 numbers together. So our strategy from up here is we just kind of add the fractional parts. If we end up with a fraction, we just leave it. If we have some whole number bits that come out of the fraction, we bring that up top, and then add the whole number parts all together. And that's our answer. The same strategy actually works here. I'm adding two numbers together, so I don't have to worry about any of this borrowing or carrying or any of that. Sorry, I don't have to worry about borrowing. I don't have to worry about breaking up a whole into smaller pieces because there's no takeaway, right? There's no idea of neutral pairs here. I'm just adding two positive numbers together. So I start with 1/4 plus 1/3, add my fractional parts together. But hey, this is a problem that I know how to do. The lowest common denominator is 12, or this is 3/12 plus 4/12, or 7/12. Did I end up with a whole? No, I didn't have more than 12 slices when I accumulated all of these together. So nope, I have just 7/12 of a pizza from the fractional parts. Then I add my wholes together, 3 plus 6. I don't have any extra wholes from the smaller slices being added together. Is 9. And then I just stick these together, 9 and 7/12. So addition tends to be much easier than subtraction. And even though this was an addition problem with where the fractional parts had unlike denominators, I think it was still a lot easier than the subtraction problem up here where the fractions had like denominators. I just added the fractions, got my resulting fraction 7/12, added my wholes, got my resulting whole, 9 whole pizzas, and 7/12 of a pizza. And that's my answer, 9 and 7/12. Okay. So what about this one? Now I have a subtraction where my two fractions, if I can select, it doesn't want to select, there we go. My two fractions have unlike denominators. Well, with any subtraction, the first thing that I want to ask is what's the relative size of the numbers? Is the thing I'm subtracting from bigger than the thing I'm subtracting off? Yeah, it is. My answer is going to be positive. My answer is going to be positive. I just do my subtraction as it stands here. So I'll start with 7/10 minus 1/4. Now here I would like to say, I would like to ask the question, do I have enough that I start with? Is 7/10 bigger than 1/4? Do I have enough pizza in the 7/10 of a pizza to give away a quarter pizza and still have some left over? If yes, I'll just do the subtraction. If no, then I have to borrow. I have to break up one of my whole pizzas to give me more pizza to satisfy how much I need to give away. In this case, and maybe you do have a gut feeling for this, 7/10 is, pretty much a whole pizza. It's near, it's certainly more than half a pizza. And a quarter pizza that I need to give away is certainly less than half a pizza. So maybe you say, okay, yeah, I think we have enough here. But we might not see that right away. So we have to do a little bit of trial and error, maybe. Maybe we have to go a step or two, and maybe we'll end up finding ourselves in a situation where we don't have enough pizza to start with, that we don't have enough to give away. And then we need to rewind a little bit, borrow from a whole pizza, break it into slices, and then proceed forward again. So again, sometimes you don't see the whole path at the beginning, but can you take a couple of steps forward? If you go down a slightly wrong path, then just back up a little bit, fix things, and move forward again. My lowest common denominator here is going to be 20, because 10 times 2 is 20, and 4 times 5 is 20. So 10 times 2 is 20, so I multiply top and bottom by 2 for that fraction. And 4 times 5 is 20, so I multiply top and bottom by 5. This gives me 14, 7 times 2, minus 1 times 5, or 5. over 20, 9 over 20 for my fractional part. So I did have um, enough pizza to start with that I could give away that 1/4 and still have some left over. I didn't need to break up any of my whole pizzas into fractional pieces. So my fractional bits, 7/10 minus 1/4 gives me 9/20. And now my whole bits, 9 minus 2 is 7. My answer is 7 and 9/20. Okay, one more example. Let's look at this one. Let's simplify 2 and 1/3 minus 3 and 3/4. I do have a subtraction problem here. I'm subtracting two positive numbers. So let me check and ask, is the thing I'm subtracting from bigger than the thing I'm subtracting? In this case, no. My answer is going to be negative. So I get a negative number for the answer. And I'm going to rewrite this as negative, and then I flip the order that I do the subtraction. It's a funky looking too. So I exchange the order that I do the subtraction, and I know my answer is going to be negative, so I remember that this negative goes in front of there. Let me come over to my scratch work and actually carry out this operation. 3 and 3/4 minus 2 and 1/3. Here, the thing I'm subtracting from is bigger than the thing I'm subtracting off. So let me look at my fractional parts. What's 3/4 minus 1/3? Or if I start with 3/4 of a pizza, am I going to have enough to give away 1/3 and still have some left over? It kind of seems like it, right? 3/4 is more than a half a pizza that I have, and 1/3 is less than half a pizza I need to give away. So I think I have enough. Let's carry out the operation. What's the LCD? Well, I know 4 is 2 times 2, and 3, its prime factorization is just 3. My LCD is going to be 12. 4 has to multiply by 3 to make 12. So I multiply my first fraction by 3 on the top and bottom. And my second fraction, the denominator of 3 has to multiply by 4 to make 12. So I multiply by 4 on the top and bottom. Or this gives me 9/12 minus 4/12, and that gives me 5/12. So I did have enough pizza when I started with this 3/4 to give away the 1/3 and still have some left over. I didn't need to break up one of my whole pizzas. I had enough in the fractional bit to start with. So I subtracted my fractional bits. Now I subtract my whole pizzas. 3 minus 2 is just 1. I glue these together to get a provisional answer, 1 and 5/12. But remember, this was just in the scratch work. My actual answer, bringing that back over here, is negative 1 and 5/12. So again, lots of steps, but if we take it one step at a time, we know anytime that we subtract two positive numbers, we always ask, is the thing we're subtracting off bigger or smaller than the thing we're subtracting from, and decide whether our answer is positive or negative. If our answer is positive, we just do the subtraction as it is, as it stands there. If the answer is negative, we flip the order of subtraction and then we make the whole thing negative. That's just something that we've always done with integers or any of that. We're in mixed numbers, but we do that same thing. that's just how we do subtraction of positive numbers. Right, when we come over here, we're asking, is the fractional part that I have bigger than the fractional part that I have to give away? If it is, then I just do that subtraction and carry it out. If it's not, then I borrow one from the bigger, from one of the whole pieces. I borrow one of the whole pizzas, I cut it into more slices. In this case, it'll be slices of a quarter. So I would turn one of my whole pizzas into 4 quarters, add that, and maybe get 7 quarters, and then do my subtraction. If I don't know, if I'm not sure whether the amount of pizza I start with is bigger than the amount that I have to give away, then I basically, kind of presume it is and start going forwards. And if I end up with, if I were to end up with 3/12 minus 4/12, well, I don't have enough to give away. So then I would just rewind. I would borrow from one of my whole pizzas, add some more quarter slices in, and go back forward again. So if I'm not sure if it's going to work out okay or not, I proceed forward. I take a couple steps forward, being very careful and cautious, not taking any shortcuts. And then if it works out, great. If it doesn't work out, well, I rewind. And now I have a new piece of information. I know that I don't have enough pizza to start with, enough fractional slices of pizza to start with. I need to break up one of my wholes to make some more fractional slices. Okay. And one last example here. This will probably be all we get through today. So example, Pat bought a bag of chocolate chips at the store. The back of the bag says the serving size is 3/4 of a cup of chips, and the bag contains about 13 servings. So this is usually on the nutrition facts panel. Pat uses 3 2/3 cups of chips in a recipe, and we want to know how many cups of chips are left over in the bag. Maybe so we know, whether we can make this other recipe, something like that. So let's first figure out what's the total amount of chips in the bag. Well, if one serving of chips is 3/4 of a cup and there are 13 servings, that's 13 times 3/4, or that's 39/4 of 39/4 cups. I should use the units, cups of chips in the bag. This is an improper fraction. Again, it's not always terrible to work with improper fractions, but in this case, maybe it will be nicer to work in whole cups because he's using, or sorry, in mixed numbers of cups, because he's using a mixed number of cups, right? If you wanted 3 2/3 cups, you wouldn't sit there with your 1/3 cup scoop and scooping all day. You would take your 1 cup scoop, you'd give 3 scoops of that, and then your 1/3 cup scoop and give 2 scoops of that, and you'd be done. So 39/4 cups. Well, I know that 9 times 4 is 36, and 10 times 4 is 40. 39 is bigger than 36, but less than 40. So this is going to be 9 whole cups and 3/4 of a cup left over. So the total amount of chips in this bag will be about 9 3/4 cups. Now Pat uses 3 2/3 cups. How many are left? So what's left after the recipe is 9 3/4 minus 3 2/3. Well, this is a mixed number subtraction, right? This is just the kind of problem we were doing up here. Is the number that we started with bigger than the number we're subtracting off? Well, hopefully. In a real life application, if you can't use more chips than are in the bag, so we have kind of a reasonability restriction here. So yeah, what we started with is more than what we took away. So we're just going to do the subtraction as is. If I do 3/4 minus 2/3, is 3/4 bigger than 2/3? Well, these are both bigger than a half. We might not really know. We might be able to think about it, right? I mean, here's 3/4 and here's 2/3. So, I mean, thinking of the pictures, okay, yeah, 3/4 is bigger than 2/3, but we might not know this right away. But we just proceed forward then. If we don't know that 3/4 is less than 2/3, or if we don't know that the first is less than the second, um, then we proceed forward as though it's going to work out. And if something breaks along the way, we'll come back and fix that later. I need to get a least common denominator, and that's going to be 12. 4 times 3 makes 12. I need to multiply top and bottom by 3. And 3 times 4 makes 12. Multiply top and bottom by 4 on this other fraction, the 2/3. Or this is 9/12 minus 8/12. And we see we just barely had enough. We had 1/12 left over. So my fractional parts, 3/4 minus 2/3, gives me 1/12. And my whole cup parts, 9 whole cups minus 3 whole cups, is 6. I glue these back together and get 6 and 1/12. That's the number of chips that are left over. He started with 39/4 cups, or 9 3/4 cups from the bag, used up 3 2/3 for the recipe. He's got 6 and 1/12 cups. I suppose I should write the unit. Mathematicians hate units, but we like to just work with numbers and forget that units even exist, but units are important. So he ends up with 6 and 1/12 cups, and then he can decide if that's enough to make whatever the recipe is, some other future recipe, or if he needs to go back to the store. Hopefully 6 cups would be enough of chocolate chips would be enough for most recipes. It'd be quite chocolatey if it wasn't. All right, any questions on anything we talked about today? So we come back next time, we'll talk about solving equations with fractions, really just applying our same old previous equation solving steps, but in the context where we might have fractions as maybe the coefficient of a variable, or maybe added on to the variable or subtracted from the variable. So just looking at section 4.7, solving equation with fractions next time. Let me end the recording.